In this talk, we are going to go over some recent theoretical results on the asymptotic optimality of task and motion planning. I'm Rahul Shome. I'm a postdoctoral research associate at Rice University, and this was work done while I was at Rutgers University with my collaborators Daniel Nakhimovich and Kostas Bekris. So how is task and motion planning relevant to real-world applications? We are increasingly seeing robots being deployed to interesting use cases like performing experiments in a wet lab, or the pandemic response, or more traditional automation applications like warehouse pick and place. In each of these instances, the robot has to achieve some sort of task objective by performing a sequence of actions or interactions, each of which will require the robot to move in a very specific and carefully reasoned way. When you bring all of this reasoning together, that entails task and motion planning. Especially with the deployment of these approaches to real world settings, it kind of underscores the importance of understanding the behavior of these algorithms and to be able to carefully describe the algorithmic choices that can lend such solutions nice, desirable theoretical guarantees. One such theoretical property, which would be the focus of the current work, is asymptotic optimality. So just to motivate our contribution very briefly, let's go over what this task and motion planning space looks like at a very high level. So it has to begin somewhere, right? So from some sort of start configuration where the robot starts off from, and you want to achieve a task objective and reach a task goal configuration. But it does not suffice to just move from the start to the goal. You actually have to hit certain intermediate transition configurations. So if the problem is to change the location of an object using a robotic arm, you might have to hit configurations which pick and place the object at the appropriate junctures. Now, each of these segments constitutes its own motion planning problem where you have to reason about how to safely move the robot. And when you think of it together, it becomes a task and motion planning problem. So at each such step, you might have different alternatives or choices of what to do next or where to go next or the next transition. And this, when brought together, gives you a set of choices in your planning algorithm. So you need to figure out the sequence of transition configurations you want to explore. You also want to figure out the best way to move between any two pairs of these transitions. And the way you do that would be with a high-level search that explores different transition configurations. And for the purposes of this talk, we will focus on asymptotically optimal roadmaps as a method for motion planning between two transitions. So the contributions of this work, just to briefly summarize, are the outlining of the minimal algorithmic design requirements that can allow us to achieve asymptotic optimality by just building asymptotically optimal roadmaps for each such motion planning component. And we show that not only is it sufficient to guarantee this property for the entire task and motion planning problem, it is also sufficient to connect between start and goal transitions that violate some of the typical assumptions that lie in both task planning as well as motion planning domains, where we can deal with such points that lie on non-smooth boundaries, and we would go into more details about why that is more important, and that's a commonly occurring phenomenon. Now, let's take a step back and let's talk about what the problem actually is, right? So what are typical robotic motion planning problems? A motion planning problem would involve D degree of freedom robot which can have D joints, say, and this describes a configuration space which is d-dimensional. And the problem is about finding a valid motion between the start to the goal. When we go to task planning, or specifically task and motion planning, the task space now includes not only the robot but additional variables, which say for an example, in manipulation, it includes the d-dimensional robot as well as the 6 degrees of freedom for each pose of the object. Now, this space is going to have a certain subset that would be valid and a certain subset that would be invalid or an obstacle. But this is going to keep changing if the poses of the object keep changing. As you can see with the red arrow, once the object has been moved, the obstacles look different. So it becomes a different planning space, right? So these different spaces are what we will call orbits, because these need to be achieved in the task space by going through specific transition configurations. So in order to change the pose of an object, you actually need to pick up an object and using some grasping configuration and potentially place it at the moved pose or the placement configuration. Now, going back to the sort of algorithms that we will focus on in this talk, uh, we need to look into sampling-based planners. Now, sampling-based planners are essentially a rich literature of algorithms that have looked into sampling the configuration space and then creating data structures that can express the connectivity of the space till the start and the goal are connected with a path. And initial work focused on probabilistic completeness, which guarantees the existence of a solution. And we got the seminal work on PRM and then later on RRTs. And more recently, we have also started focusing on quality guarantees, where we have devised the theoretical conditions necessary for motion planning to converge to the optimal solution. So now that we have described sampling-based planners, what does asymptotic optimality mean for sampling-based motion planning? It expresses the theoretical guarantee that as the number of samples increases, the solutions that you can discover will get closer and closer in terms of cost to the optimal solution cost. Now, one such algorithm of interest is PRM star, which is the asymptotically optimal variant of probabilistic roadmap methods. In this algorithm, we connect neighborhoods of sampled configurations parameterized by a connection radius. Work by Karman and Fazoli had shown that when this connection radius follows a specific functional form in terms of the number of samples, we can achieve asymptotic optimality. Now, in terms of sampling-based approaches that have been devised for task and motion planning, lines of work that have been done in the past have tried to break the problem into a high-level search over different planning subspaces that need to be traversed to reach the task goal. And within each such subspace, there is a exploration of different ways to move the robotic system. So we choose the notation of calling these subspaces orbits, as has been also used in prior work, but different alternate notations also call them constraint manifolds or factored spaces. Now, out of these, Vega Brown et al. Actually focused on a formulation of this algorithmic framework and the properties that afforded asymptotic optimality. So the first thing we do as a contribution is to find the common features of the different ways people have devised task and motion planning algorithms that allow us to argue asymptotic optimality. So we begin from a start configuration and the orbit it belongs to and add it to a search tree over orbits. Now, in each iteration of the high-level search, we shall select a random node of the search tree, and for each such selected orbit that corresponds to that node, we shall first expand a constant number of transition configurations that allow us to go into adjacent orbits. We shall also expand a constant number of configurations in the interior of the orbit that can grow a roadmap. Now, once the roadmap connects to a transition configuration, it can be added as a new orbit in the search tree. And this process keeps repeating with new transitions being added and a growing roadmap connecting more and more orbits and adding more orbits to this tree of orbits. So eventually we would like to expand an orbit that will contain the task goal configuration. Now, this allows us to express a search structure which consists of orbits, transitions between orbits, and roadmaps being constructed inside each orbit. And now we can focus our theoretical insights on such a search structure. Previous work by Vega-Brown et al. Narrowed down the theoretical conditions necessary for task and motion planning to be asymptotically optimal. They argued that you need to construct roadmaps within each orbit that uses a connection radius that is twice that required by PRM star for motion planning. Now, since this radius is now larger, the computational load is also expected to be much heavier because you would be evaluating more edges. So the question now becomes, is such an inflation of radius necessary? And that is where our contribution lies in identifying that we do not need to inflate the radius of an asymptotically optimal roadmap within an orbit in order to achieve the same property in the task and motion planning space. So if you construct a PRM star with its normal radius, you would achieve asymptotic optimality for task and motion planning as well. So a brief sketch of this proof or the sequence of arguments that we followed involve first going back to the original work by Vega-Brown, where he showed that there exists a sequence of paths which describe task and motion planning solutions that would have very small errors with respect to the optimal task and motion planning solutions. And these solutions will pass through certain positive volume transition regions within which all the task and motion planning solutions will share a very small error with respect to the optimal cost. Now, what this lets us do is, this lets us describe the problem in terms of ensuring that we sample across these transitions, and then for each such pair of samples, if we can guarantee that the roadmap within the orbit can connect these two samples asymptotically optimally, we can achieve asymptotic optimality for the entire path. The next step in this argument uses a previous result from SST star. So the orbital search tree we construct in our algorithmic outline resembles a random tree which selects nodes uniformly at random. using the previous result, we can guarantee that each node is given infinite opportunities to be selected, which implies each orbit will grow the roadmap infinitely often and will add transitions infinitely often. This has the effect of guaranteeing that the roadmap becomes asymptotically optimal and connects pairwise transitions asymptotically optimally. And we are also then assured to sample in each possible positive volume region of transitions. So since we have shown that a desirable sequence of regions of transitions already exists, tracing which we can guarantee asymptotic optimality, the result follows. And this concludes the sketch of the proof. So the next contribution that we make is about specifically the boundary points or the start and the goal transitions in each orbit. Now, typically in motion planning, as well as in the previous work on task and motion planning, these points have been assumed to be either in the interior of the space or on smooth boundaries. Now, the key observation here is this assumption is violated very readily in practice. And this is evident from the toy example that is shown in the figure on the right, where a toy gripper that is free to move in the x-axis with the dimension g representing the opening of the fingers, the point of grasp will lie at the apex of a triangle, which is necessarily not smooth. And this kind of geometric contact is expected to happen a lot for typical task and motion planning problems where the robot interacts physically with the environment. So the question now arises, can we reconcile the theoretical modeling of this problem to explain or address these boundary points which might not lie on smooth boundaries? So what we do is we model the start and the goal points as being attached to hypercones that open up into a smooth interior of the space. And it turns out that with this very small change of the framing of the problem, it is sufficient to guarantee that the normal properties of asymptotic optimality of planning within the space as well as for the task and motion planning space readily still work out. A very high level intuition behind the series of arguments is shown here. So what we do is we have these hypercones attached to the start and the goal points of the orbit, and then we have the smooth manifold interior with which these hypercones have a positive intersection. So we want to argue that a asymptotically optimal roadmap growing within the orbit is going to eventually connect the start to the goal. So the typical asymptotic geometric construction in a roadmap tiles hyperbolas in the interior of the space, and we still do that, but we do that till the opening of these hypercones. And the only thing we need to show is not only is the algorithm or the roadmap assured to drop samples in each of these hyperbolas, but also in a constant number, or in the specific case, 2 hypercones. And it turns out that this is readily handled by the standard radial bounds for asymptotic optimality, and sampling across such constructions is assured, which means that using the connection radius of something like PRM star is still going to work. And it should also be noted that we can also use other asymptotically optimal roadmaps like FMT star, which uses a slightly smaller connection radius but gives a slightly different kind of asymptotic convergence. Now, of course, there are some things we have not addressed in the current work. Even though we have relaxed some of the assumptions from previous work, we still leverage some of the considerations that require the spaces that we described to be well behaved. And our reliance on roadmaps also limits applicability to kinodynamic domains. We also admit that the algorithmic outline that we have described is kind of bare bones and will not have any efficiency guarantees because the space of possible transitions and orbits can grow intractably large. So we need efficient heuristics to guide such a search in practice. We also need to explore more interesting cost functions and other non-analytic constraints that can describe orbits and potentially encode more complex transition costs between orbits that can express more interesting task interactions. To conclude, I would like to reiterate our contributions. So in this work, we have shown that when you're designing a task and motion planning algorithm, as long as you can guarantee that you're building a search tree that asymptotically explores all possible orbits and transitions, and within each such orbit, it constructs an asymptotically optimal roadmap, then you're guaranteed to be asymptotically optimal in task and motion planning. We additionally relax the assumption that start and goal transition configurations within each such orbit need to be on smooth boundaries of the free configuration space. Finally, I would like to thank Daniel and Kostas, my collaborators, for their invaluable help during the course of this work. And I would like to urge all the listeners and viewers to refer to our paper for additional details and clarifications. Thank you.